This video is going to give you some tools to proving trigonometric identities. And the first thing we need to understand is the logic behind our proofs. So we have to do one of three things to prove that A equals B. Either we have to take A and convert it into B, or we have to take B and convert it into A. That's actually kind of the same thing. It just changes what side you start with. Or there's a third option. Sometimes when both sides are fairly complicated, it's easiest to convert one side into C and convert the other side into C. And then if they're the same, then we know the first equation was true. So students often ask, why can't you just work with the equation? Why can't we take the equation and play with it until we get something true? And logically, you just can't start a proof by stating something that you're trying to prove. You can't start with something that you don't know is true. So for example, let's say we didn't know that -3 was actually not equal to 3. Let's say we didn't know whether it was true or not. We secretly know it's not true, but let's just pretend we don't know this. I can actually take this equation and do a proof with it. If I start with the fact that -3 equals 3, I can square both sides, and then I end up with an equation that's true. So -3 equals 3. Awesome. But of course, that's not true. And the reason it's not true is because our proof was flawed to begin with. Can't start with the equation you're trying to prove. All right, so let's go ahead and talk about the methods to use. With trig equations, there's a variety of things that will work sometimes and not work other times. So what are the tools we have? Using identity, like the Pythagorean identities, changing everything to sines and cosines, getting common denominators, factoring, and reducing goes with factoring, and something that I call the trick, which we'll look at as our last example. All right, so let's actually do an example. If I want to prove that this identity is true, I need to take A and turn it into B, or B and turn it into A. I'm going to go ahead and choose this left-hand side to start with because it's uglier. I always choose the uglier side to start with. So here's my proof. I'm taking that side. I'm going to go ahead and get common denominators. I'm starting with this tool because I have two fractions and I'm subtracting them. So when I do that, this is the next fraction I get. When I distribute the negative, of course, I get a plus sign of phi, and the ones cancel each other, and I end up with 2 sine phi over 1 minus sine squared. So what do I do next? Well, I just use an identity where 1 minus sine squared and cosine squared are the same thing. That's the Pythagorean identity. Then I'm going to go ahead and break it apart into 3 different factors, 2 times sine of phi over cosine of phi and times 1 over cosine phi, and that's exactly what I wanted up here. And I'm done with my proof. So let's look at another example. This definitely looks like the ugliest side, so let's start there. I'm going to go ahead and change everything to sines and cosines first because I don't see any identities necessarily. And when I get common denominators on the top and the bottom, right, there's the numerator, and then I have to do the denominator too. I end up with a big, huge division problem. And when I do that division problem, right, flip the denominator and multiply, I end up with this lovely thing right there. Now what to do next? Well, I still don't see any identities. I've already changed everything to sines and cosines. There's no denominator to make common, but can I factor? Aha, notice there's a sign in the numerator and a sign in the denominator. I can actually factor a sign out of the numerator and denominator, and then I can reduce. And I end up with cosine squared a minus 1 over cosine a minus 1. Wow, I'm not exactly sure what to do next. There actually are things we can do, but let's pretend we get stuck there. So let's actually do this process. Let's say we get stuck there, let's start with this guy. So sine squared over 1 minus cosine, let's play with that. Aha, there's an identity. Sine squared of a is actually equal to 1 minus cosine squared a. And I can rearrange that, multiply top and bottom by -1, and now these guys are actually equal. So the original identity was equal. And here's an example of the trick. Let's prove this. Well, there's almost nothing to do. How do I even start playing with this? There's no identities. It's already changed to sine and cosines. There's no common denominator to do. There's no canceling, no factoring. So that's why we need the trick. What we're going to do is multiply top and bottom by 1 plus sine of b. If you notice when we do this, this denominator is going to become 1 minus sine squared b. It's a little bit like multiplying by the conjugate of imaginary numbers or complex numbers. It's not the same thing, but it's kind of analogous. And when we do that, we can actually use the Pythagorean identity that 1 minus sine squared is actually cosine squared, and now we can reduce. Because if we cancel one of the cosines, we end up with 1 plus sine b over cosine b. This is just something that we need to keep in mind whenever we get stuck, especially if we have something like 1 minus sine b to play with or 1 plus sine b. And the same thing goes with cosine. There's the trick, and we've done it.